Hello everyone and welcome to the solution manual for GP6. Starting with question number 1. It talks about a long play vinyl record format which has a diameter of 12 inches and is played at a frequency of 33 revolutions per minute. Now part A is asking us to find the frequency of the record in hertz, which is the same as revolutions per second. We know that 1 minute has 60 seconds in it, so we take our revolutions per minute. 1 minute has 60 seconds in it, and we get our answer as 0.55 revolutions per second, or hertz. Now part B is asking us how long does it take the record to complete 3 full revolutions. We know that the frequency is 0.55 hertz, and so we can find the time period as just the inverse of the frequency, which is 1 over 0.55, which gives us approximately 1.82 seconds, and that's how long it takes to complete 1 revolution. So the time taken for 3 revolutions is just 3 times the value that we found, which gives us around 5.45 seconds. Now part C is asking us to find the angular velocity of the record. So we know that the angular velocity from, I think, the 4th point at the top, we have the absolute value of the angular velocity as 2 pi times the frequency, which is just 2 pi times 0.55, which gives us 3.46 radians per second. But remember that this is moving in the clockwise direction, and according to our convention, clockwise is negative, meanwhile anti-clockwise is positive. So the value of our angular velocity is finally minus 3.46 radians per second. So this negative comes again from the fact that it's going clockwise, and radians per second is the units. The part D for question number 1 talks about imagine placing a penny at the edge of the record. The penny does not slide off but rotates with the record at a constant speed. What is the speed of the penny in meters per second, recalling that 1 inch is 2.54 centimeters? Okay, so it completes the circumference in 1 period, right? 1 revolution in 1 period, and the revolution of a circle is the circumference. So the velocity, which we know as distance over time, the distance or the circumference for a whole circle is 2 pi r divided by the time, and we know the time is just the inverse of the frequency, or the other way around, so we can just get 2 pi rf as the velocity, which then equals to 2 pi. Now we have been given the diameter, I think, as 12 inches, so the radius becomes 12 divided by 2, which is 6 inches. We know that 1 inch has 2.54 centimeters in it, so 1 second. We know that 1 inch has 2.54 centimeters in every 1 inch, and we know that every meter has 100 centimeters in it. And so now this is in meters. The radius is now in meters. Multiplying this with the frequency gives us a value of 1 second, gives us a value of approximately 0.53 meters per second. And that is the angular velocity, or sorry, not the angular, that is the speed of the pen. Yep. So for question number 2, we have a crazy motorcyclist riding at a constant speed in a vertical loop of radius 2.5 meters. So we have a radius of 2.5 meters. The combined mass of the motorcycle and rider is 250 kgs. And for part A, we have been given a period of rotation at 1.5 seconds, and we need to find the centripetal acceleration. So the centripetal acceleration can be found using the same formula we used before, which is v squared over r. We have been, and velocity is distance over time. To complete an entire I guess a revolution of this loop, the distance traveled would have to be 2 pi r, that's the circumference, by the time. And so our acceleration becomes 4 pi squared r, just r, because that gets cancelled, by d squared. And then plugging in the values, we have 2.5 for r, 1.5 for t. You should get a value of around 43.9 meters per second square. For part B, it's asking us to draw a free body diagram for the cyclist at the bottom of the loop. So the free body diagram should end up looking like this. There is the force of gravity acting on the cyclist or the motorcyclist. The centripetal acceleration points upwards towards the center again, since he's going like this. It's pointing up, and so the net force is also pointing upwards, and so your other force, your F normal, or your net force here, points upwards. And this is the free body diagram. Here the normal force has to be greater than the Fg, since there's the centripetal acceleration acting towards the center as well. And so this is your free body diagram. And now we have part C. Actually, let me just go down. Now part C requires us to find the magnitude of the normal force on the cyclist. We know that F net, the net force acting on the cyclist, is just m times the centripetal acceleration, and we can rewrite this as the sum of the components, which is the normal force minus the gravitational force. And by putting Fg on that side, we can find the value of Fn, which is just MAC plus mg. Now we know the value of m, which is just 250. AC is 43.9. Let's take G to be 10. We get 53.9. And solving this gives us a value of approximately, it gives us 13,400 66 newtons. So this is the magnitude of the normal force at the bottom. Part D. Now that the cyclist is at the top here, it's asking us to draw another free body diagram. So at the top, Fg still acts downwards, And centripetal acceleration now is still pointing towards the center, but center is down. So your normal force is also pointing down. As you can see, it makes contact with the surface at the top here, so N is going down as well. And so based on this, we have question number E, which is the same question as part C. But now, since the direction is opposite, we have our Fn as MAC minus mg, which is equal to 250 times 43.9 minus 10 is 33.9. And solving for this gives us a value of 8,466 newtons, I think. Yeah, 66 newtons at the top. Now, part F is asking us, at what position is the apparent weight of the cyclist larger, when she's at the bottom or the top of the loop? So apparent weight is just the magnitude of the normal force. So if we look up here, the magnitude of the normal force at the top was 13,000, at the bottom it's 8,000 basically. So the apparent weight is larger at the top. Oh, sorry, at the bottom, not at the top, because 13,000 is bigger than 8,000. Now moving on to part G, we have, if the cyclist reduces her speed, which force gets smaller in the free body diagram that we drew in part D? So which is at the top. So again, Fg is a constant because g is a constant. And by reducing the speed, the only thing that's going down, constant, is AC. AC is reducing its value, so the only thing that is going to reduce its magnitude would be the normal force. Normal force reduces when the cyclist reduces her speed, or his speed. Question H talks about, is there a limit to how small this force that you identified in part G can get? And what happens if the cyclist reduces his speed even more? Yes, there is a limit actually. So the normal force must be greater than or equal to 0. Normal force can never be negative. That doesn't happen. And if the normal force does get lower than its minimum, then the cyclist just falls from the top. That's it. She just falls and breaks her neck probably. And we have the last part of question 2, part I. Given your answer in the previous part, what's the minimum speed at which the cyclist can make it to the top of the loop without falling off the loop? So we need to find the minimum speed of the cyclist now. So we have, so if you want to find the minimum speed, let's set Fn to be 0. And all that leaves us then with is MAC equals to mg. So cancel this, it's just left with AC equals to g. So v squared over r equals to g. And so we can find v min. Put r on the other side, take the square root, you just get square root of rg. And your radius is how much again? I think 2.5 meters? Yes, 2.5 meters, so we take the square root of 2.5 multiplied with 10, which is 25, and square root of that is just 5 meters per second. That's your minimum speed. Alright, so for question number 3, we have been given a turning car that has a mass of 1200 kgs, and it's trying to take a turn around a level circular track of radius 20 meters at a constant speed v. And they've given us a bird's eye view on the right there. So question A is asking us what what force is responsible for the centripetal acceleration? So the force that is responsible for the centripetal acceleration is static friction, which is pointing radially inwards. So if we take our circle, so let's just say that the car is driving on this track, it's over here, and the center of the circle is somewhere over there. Static friction will point towards the center like that. And if, yeah, and so, yeah, so that's just static friction over there. That's responsible for your centripetal acceleration. Part B is asking us to draw a free body diagram of the system where the y-axis is vertical and the x-axis is horizontal. So on this car, there's a normal force that is coming out of the page like this, and there's a gravitational force that's going into the page like that, and there's your Fs going like this. So to represent this in terms of a free body diagram, we can write it like this. So we will draw our y-axis, and we'll draw our x-axis. And this is your normal force pointing vertically up, gravitational force pointing vertically down, and your force of static friction pointing radially inwards towards the center of whatever arc the car is traveling. Moving on to part C. Part C and D are quite similar, but let's go to part C, which says if the coefficient of friction between the wheels and the road is now, so that the coefficient of friction is now 0.3, what is the maximum speed? So what is V max that it can travel without sliding? So we found here Fg and Fn, and we have Fs over here. The centripetal force that's acting on this car can be written as mv squared over r, because mac and ac is v squared over r, and the normal force that's acting on this is the coefficient of static friction times mg. So in order to get the value for v, we equate fc equals fn and solve, and we get v max squared over r equals to mu mg. Mu mm gets cancelled, and we're left with v squared v max squared over r equals mu g. And now we need to find v, so v max is finally mu r g square root, and solving for this gives us 0.3. The radius is 20 meters and g is just 10, so that's 200, so that gives us approximately 7.7 meters per second as the maximum velocity of your car that it can go without slipping if the coefficient of friction is 0.3. And finally, moving on to the last part of question number 3, we have, oh, that's not how you write a D. Moving on to the last part of question 3, we have, now they've given us the velocity at 13.4 meters per second, and they're asking to find the minimum coefficient of friction. So we can use the same equation that we found up here again. So let's just write that down. So v squared over r equals to mu min g. And we can solve for mu min by doing mu min equals to v squared at the top and r g. Plugging in the value of v squared as 13.4 squared divided by 20 times 10 gives us our final answer for the minimum coefficient of static friction to be around 0.898. And so the coefficient of, so what this means is it must be either this or the car will slip. So the coefficient of friction needs to be at least 0.898, otherwise the car just slips off the road. And I think that covers group problem 6. If you have any doubts or any questions, please feel free to reach out to me. My name is Akshat. I'm going to write my email right here for any questions or anything at all. And thank you for attending the group problem session today.